We shall commence this module by discussing about multivariate function. Multivariate functions are the ones which allow more than two variables to be analyzed at a time. The subject of multivariate analysis deals with the statistical analysis of the data collected on more than one response variable. Probabilities may be either marginal, joint or conditional. Understanding their differences and how to manipulate among them is the key to success in understanding the foundation of statistics. After studying this module, you shall be able to 1. Understand the joint and marginal distribution of probability functions. 2. Analyze more than one statistic at a time. 3. Know the conditional distribution for multivariate functions. 4. Know the independence and dependence for multivariate functions. Now we will be discussing about joint probability. When joint probabilities are assigned to two or more random variables, the resulting relationship is known as the joint probability distribution. Joint probability distribution of two random variables are referred to as bivariate distribution, and for more than two random variables, the distribution is said to be multivariate. The joint distribution is defined for both continuous and discrete variables. Moving on to the continuous multivariate random variable probability distribution, we have that if x1, x2 to xk are k random continuous variables, then given the joint probability density function as f is equal to x1, x2 right up to xk exists, we have probability of x1 that is greater than equal to a1, which is less than equal to b1, and x2 is greater than equal to a2, which is less than equal to b2, and this goes up to xk, which is greater than equal to ak, and bk is greater than equal to xk. Integration of a1 b1 and again integration of a2 b2 right up to integration of ak bk of the function x1 x2 to xk dx1 dx2 right up to dxk. Also, if f function of x1 x2 to xk should satisfy, first the function x1 x2 right up to xk is greater than equal to 0 for all values of x1 x2 right up to xk, and integration of minus infinity to plus infinity, again integration of minus infinity to plus infinity right up to integration of minus infinity to plus infinity of the function x1 x2 up to xk into dx1 dx2 right up to dxk is equal to 1. For the special case of bivariate distribution, if the joint probability density function f x1 x2 of the two random variables of x and y exists, then the probability of x1 greater than equal to a1 less than equal to b1, x2 greater than equal to a2, which is less than equal to b2, is equal to integration of a1 to b1 integration of a2 to b2 a function of x1 x2 dy dx. Next, we discuss the multivariate distribution function, the joint distribution function of the k-dimensional random variable x1, x2 to xk is defined as a function of x1, x2 to xk is equal to integration minus infinity to xk into minus infinity to xk minus 1, which goes up to minus infinity to x1 of the function u1, u2, uk, du1 right up to duk for all x1, x2 to xk corollary. Also, if the joint distribution function is continuous everywhere and partially differentiable with respect to x1, x2 to xk for all but a finite set of values, then f function of x1, x2 to xk is equal to del k, del raised to the power of k divided by dx1, dx2 to dxk, a function of x1, x2 right up to xk, wherever these partial derivatives exist. In case of bivariate distribution, f x1 x2 is equal to probability of x1 greater than equal to x1 and x2 greater than equal to x2, which is equal to integration of minus infinity to x2 into integration of minus infinity to x1 function of u1 u2 du1 du2, where x1 lies between plus infinity and minus infinity and x2 also lies between plus infinity and minus infinity, where f u1 u2 is the value of joint probability function of x1 and x2 at u1 u2. Properties of the joint distribution function f x1 x2 is: first, function of minus infinity comma minus infinity is equal to the function of minus infinity x2, which is equal to the function of x1 minus infinity, which is all equal to 0. Second, the function of infinity infinity is equal to 1. If b is greater than a and d is greater than c, then the function of ac should be less than the function of bd. Deriving a distribution function from a joint density function. Consider a joint density function for x1 and x2, which is given by fxy is equal to x plus y, where x is greater than 0 and should be less than 1, and y is greater than 0 and should be less than 1, it is 0 elsewhere. With the given assumption, the function has a positive value in the square bounded by the horizontal and vertical axis in the first quadrant, with its four corner points being 0, 0, 0, 1, 1, 0, 1, 1. It is 0 elsewhere. We find that the distribution function by integrating the joint intensity density. There are five different cases. If either
x1 less than 0
or
x2 less than 0,
it follows that f x1 x2 is equal to 0. Second, if
x1 is greater than 0 and less than 1,
and
x2 is greater than 0 and less than 1.
we get fx1 x2 double integration. First is 0 to x2, then 0 to x1, s plus t ds dt is equal to half x1 x2 bracket open x1 plus x2. For x1 greater than 1 and
x2 is greater than 0 and less than 1.
we get fx1 x2 is double integration 0 to x2 0 to x1 s plus t ds dt is equal to half x2 bracket open x2 plus 1. For
x1 is greater than 0 and less than 1.
and x2 greater than 1, we get f x1 x2 double integration 0 to 1 0 to x1 s plus t ds dt, which is equal to half x1 bracket open x1 plus 1. First, and for x1 greater than 1 and x2 greater than 1, we get f x1 x2 is equal to double integration 0 to 1 0 to 1 s plus t ds dt equal to 1. Further, we discuss discrete multivariate random variables probability distribution. If x1, x2 right up to xk are k random discrete variables, then given the joint probability mass function p x1, x2 to xk, we have p x1 is equal to x1, x2 is equal to x2, and xk is equal to xk. That is summation x1, summation x2 right up to summation xk into probability of x1, x2 right up to xk, where x1 lies between plus infinity and minus infinity. x2 also lies between plus infinity and minus infinity. xk also lies between plus infinity and minus infinity. Also, p x1 x2 to xk should satisfy that p x1 x2 xk is greater than equal to 0 for all values of x1 x2 right up to xk, and that summation minus infinity to plus infinity, again in summation of minus infinity to plus infinity right up to summation minus infinity to plus infinity, probability of x1 x2 xk should be equal to 1. Again, over here, when we talk about bivariate probability distribution, then given p x1 x2 is the joint probability mass function, we have probability x1 equal to x1 and x2 equal to x2, which is equal to probability of x1 and x2. Once the joint probability mass function has been determined for discrete random variables x and y, calculating joint probability involves x and y is simple. As a simple illustration for a two discrete variable case, in a toss of three coin, let x denote the number of heads occurring in three trials. Thus, x is equal to 0, 1, 2, 3. Let another random variable y be defined as follows. If the first of the three tosses results in the occurrence of heads, then y is equal to 0. If it results in the occurrence of tail, y is equal to 1. Thus, the range of y is 0, 1. The possible values of x and y and their respective probabilities are listed in the table. Consider now the probability that in a trial of the experiment, x assumes the value of small x and y assumes the value of small y. Symbolically, this may be written as probability of capital X equal to small x, capital Y is equal to small y, which is equal to probability of xy, which is the probability of the intersection of the events capital X equal to small x and capital Y equal to small y. Thus, from the previous table, we can make a bivariate probability distribution or the joint probability distribution of x and y for the experiment. This table is specified by listing the probabilities associated with all possible pairs of values x and y. In the table, the sum of the probabilities in the last row or column is equal to 1. In general, we may write this condition as summation x summation y is a function of x y which is equal to 1, where the double summation sign summation x summation y indicates that the entries in a joint probability table are added over all possible pairs of values x and y. Also note that the probability distribution function py of y appearing in the lower margin and the probability distribution of px of x appearing in the right hand margin of the table are the marginal distributions of x and y. Find one p x plus y greater than 2 and second p x plus y less than equal to 1. First, the event that x plus y is greater than 2 is composed of the pairs of the values 2, 1, comma 3, 0, 3, 1. Adding their corresponding probabilities from table, we get p x plus y greater than 2 is equal to p 2, 1 plus p 3, 0 plus p 3, 1, which is equal to 1 by 8 plus 1 by 8 plus 0, which is equal to 2 by 8. Second, in the event that x plus y less than equal to 1 is composed of the pairs of values 0, 0, 0, 1 and 1, 0, adding their corresponding probabilities from table 9.2, we get the probability that 1 is greater than equal to x plus y is equal to p0, 0 plus p0, 1 plus p1, 0, which is equal to 0, 1 plus 8 plus 1 plus 8, which is equal to 2 by 8. Now we shall discuss the joint distribution function. The joint distribution function or the joint cumulative distribution function of x and y is given by fxy is equal to probability small x greater than equal to capital X and small y greater than equal to capital Y, where x lies between plus infinity and minus infinity, and y also lies between plus infinity and minus infinity, where PUV is the value of the joint probability function of x and y at UV. Example, in the event of tossing the three coins, find F21. From the formula of distribution function, we have F21 is equal to probability 2 greater than equal to x, 1 greater than equal to y. This is given by P00 plus P01 plus P10 plus P11 plus P20 plus P21, which is equal to 0 plus 1 over 8 plus 1 over 8 plus 2 over 8 plus 2 over 8 plus 1 by 8, which is equal to 7 by 8. Now we will be talking about marginal distribution. Marginal distribution is the individual distribution of one variable and is derived from the joint probability distribution. Thus, it may be thought of as an unconditional probability. If the joint distribution of n random variables x1 to xn are known, then the marginal distribution of any kth random variable can be derived from this joint distribution by integrating or summating over all possible values of the n variable, keeping the kth constant fixed at the specified value xk. The marginal densities are obtained by integrating the joint density for the n-dimensional random variable x in bracket x1, x2 to xn. Thus, the marginal probability distribution of the kth random variable is the probability distribution of the individual xk variable and is equal to fxk, which is in bracket xk, which is equal to double integration minus infinity to plus infinity, minus infinity to plus infinity, right up to minus infinity to plus infinity of function x1 to xn, dx1 right up to dxk minus 1, dxk plus 1 right up to dxn. In case of a bivariate distribution, when x and y are jointly continuous random variables, the marginal probability density functions fx and fy are fxx is equal to integration minus infinity to plus infinity fxy xy dy, keeping x fixed within the range of x and integrating the joint probability density function pxy over all possible values of y. fyy is equal to integration minus infinity to plus infinity fxy xy dx, keeping y fixed within the range of y and integrating the joint probability distribution function pxy over all possible values of x. Marginal distribution for discrete random variables. The marginal probability distribution of the kth random variable in the nth dimensional random variable x, x1, x2 to xn is the probability distribution of the individual xk variable and is also equal to pxk is equal to summation x1 to summation xk minus 1 to summation xk plus 1 to summation xn probability of x1 x2 right up to xn. In case of a bivariate distribution, when x and y are jointly discrete random variables, the marginal probability mass functions px and py are px is equal to sigma y pxy, keeping x fixed within the range of x and summing the joint pmf pxy over all possible values of y. Similarly, py is equal to summation x pxy, keeping y fixed within the range of y and summing the joint pmf pxy over all possible values of x. Thus, given pxy greater than 0 in the example of a throw of three coins, to compute the marginal probability of x, we have x is equal to 0, 1, 2, 3, where p x is equal to 0, summation y p0y is equal to p00 plus p01, which is equal to 0 plus 1 by 8, which is equal to 1 by 8. In a similar manner, we can calculate px is equal to 1, px is equal to 2, px is equal to 3. Thus, in the present case, we have four conditional distributions of given x. A conditional probability distribution describes the probability that a randomly selected person from a subpopulation has the one characteristic of interest. Conditional probability functions for continuous distributions. Given two continuous random variables x and y with joint probability density function fxy and marginal density functions fx and fy respectively, the conditional probability density function of x given capital Y is equal to small y is defined to be fxy is equal to fxy divided by fy provided fy is greater than 0, and similarly fyx is equal to fxy by fx provided fx is greater than 0. Conditional probability function for discrete distribution. Given two discrete random variables x and y, the conditional probability that y takes on the value of small y given that x has the value small x is probability bracket open capital Y is equal to small y divided by capital X equal to small x, which is equal to probability small y by x is equal to probability of capital X equal to small x comma y capital Y equal to small y bracket close divided by probability of capital X equal to small x for p x is equal to x greater than 0. In general, if x is fixed and y varies overall possible values within the range of y, then py by x is equal to pxy divided by px for px greater than 0 is the conditional probability of the random variable y, that is the univariate distribution of y given that the condition that x has the value of small x. Similarly, px by y is equal to pxy divided by py for py greater than 0 is the conditional probability distribution of x given capital Y is equal to small y. Thus, in the example of a coin tossing experiment, the conditional probability of x given y is equal to 0 is obtained by dividing each of the joint probabilities of px0 listed in the second column of table by the fact that py equal to 0, which is equal to half. The conditional probability distribution of x given y is equal to 1 is computed similarly by dividing the entries in the third column of table by p y is equal to 1, which is equal to half. Conditional probability distribution of x for a coin tossing experiment is shown in the table. A similar conditional probability table may be constructed for the four separate conditional distributions of y, each corresponding to one of the possible values of x. Now we will be talking about independence. Two random variables x and y will be statistically independent if and only if each element in their joint probability distribution can be expressed as the product of the corresponding marginal probabilities, that is, marginal PDFs or PMFs. Also, from the conditional probability distribution theorem above, it can be seen that this condition holds if probability x by y is equal to probability x, or if probability y by x is equal to probability y. Continuous bivariate random variables. If x and y are continuous random variables with the joint probability density function fxy and marginal density functions fx and fy respectively, then from the above definition of independence, x and y are independent if and only if fxy is equal to fx into fy for all pairs of real numbers x, y. Discrete bivariate random variables. If x and y are discrete random variables with joint probability mass functions, probability xy, and marginal functions px and py respectively, then from the definition of independence, x and y are independent if and only if pxy is equal to px into py for all pairs of real numbers xy. If x and y are not independent, they are said to be dependent. The notion of independence can be extended to any number of random variables. Thus, the random variable x1, x2 to xn are statistically independent if the condition prob p x1, x2 to xn is equal to px1, px2 right up to pxn holds for all values of x1, x2 right up to xn. In the example of tossing the coins, it is clear that pxy is not equal to px into py, and hence x and y are not independent variables. Taking the case of x is equal to 1, y is equal to 0, we have p10 equal to 1 by 4, px1 is equal to 3 by 8, and py0 is equal to half. Thus, px1 py0 is equal to 3 by 8 multiplied by 1 by 2, which is equal to 3 by 16, which is not equal to 1 by 4. If px by y is not equal to px, then py by x is not equal to py. Thus, the two random variables x and y are dependent. Let us summarize what we have learnt in this module. A discrete multivariate distribution is used to model the joint behavior of many discrete variables. Similarly, a continuous multivariate distribution is used to model the joint behavior of many continuous variables. The term marginal variable is used to refer to those variables in the subset of variables being retained. The marginal distribution of a subset of a collection of random variables is the probability distribution of the variables contained in the subset. In a two variable case, the marginal probability distribution of a random variable is the univariate probability distribution which appears on the margin of the joint probability distribution from which it is derived. A random variable is said to be independent only if its conditional probability distribution is equal to its marginal distribution. In a bivariate distribution, probability is assigned to the intersection of the two random variables and the total sums up to unity. P x is equal to a by y is equal to b is the conditional probability that x is equal to a given y is equal to b.